Good morning, everyone, and welcome to the 12th and last talk of the first semester of this cycle of conference entitled Chemistry, a Hand Outreach to Society. We are about to finish the first group of talks of the first semester, and I am very proud to say that all of them have been excellent in terms of content, the interest of the topics, and the divulgative character of all of them. Our speaker today is Reynier Suardíaz de Rio from the Physical Chemistry Department, and the title of the talk is Understanding Enzyme Activity Behind Antimicrobial Resistance to the Last Resort Antibiotic Colistin. As I usually mention when I introduce these talks, we have chosen the online format instead of the face-to-face, taking advantage of the platform provided by General Foundation of the Complutense University, to whom I want to thank the help and support to organize this activity. We thank also to our funding sources, the Spanish Biochemistry and Molecular Biology Society, the Royal Chemistry Society, Sectorial of Madrid, and Vice Rector of Research and Transfer, for the financial support, because this enables us to use this format, and this way many more people can be connected. Our junior researchers, who have been investigating different aspects of the chemistry and biochemistry, return to our institution after spending a long period abroad. One of the reasons we organize these seminars in English is because they are very familiar with the use of English to report their scientific results. In this way, we can broaden our audience to foreign institutions, some of which have been the host institutions for these researchers. The lectures will continue on 2022, probably, and the program will be announced in the next weeks. I remind the students who have been enrolled for credits of this activity that they should email me at the address that I will include also in the chat. Without further ado, I give the turn to the moderator of this talk, Javier Oiz, professor of the same department, who will introduce our speaker. He also will moderate the discussion at the end of the talk and ask Reynier those questions that you can write in the Preguntas and Respuestas button. But also, if somebody wants to ask questions orally, please raise your hand. You can do it in that way. Then, now, Javier, is your turn.
Right, thank you very much. Well, it is for me a great pleasure to introduce you, Reynier. And he has a very large and a very vast curriculum already, and that gives an idea of the quality of the work he has been done along the years. Reynier is graduated in chemistry at the University of La Habana in Cuba, and he was immediately appointed as Profesor Ayudante. And in 2005, and between 2005 and 2009, he was Profesor Ayudante at the University of La Habana with a PhD scholarship at the University Autónoma of Madrid. And he finished his PhD in 2009 in the Autonomous University in Madrid. And the subject of his thesis was development of computational method to improve protein structure determined by MNR. And came back to Cuba again as assistant professor, the equivalent of Profesor Ayudante Doctor at the University of La Habana. In 2010, he obtained the postdoctoral fellowships at the University of Cambridge, and working in a similar topics as his PhD, but this time in nucleic acids. In 2011, he moved to the University Autónoma, but this time of Barcelona, with another fellowships, and he started to work in multi-scale techniques combining different levels of theory to study large system of biology relevance. He spent 2.5 years in the Autónoma of Barcelona. In 2014, he was granted by a Federation European Biochemical Societies fellowships at King's College, and here starts his period of stay in the United Kingdom. First of all, in the King's College, as I say, and shortly after he got an individual senior level Marie Curie fellowships, also in the King's College. He was appointed as Senior Research Fellow at the King's College London until 2017, and then he moved to the University of Bristol as Associate Researcher. Finally, he leaves Bristol in 2019 to lead computational modeling line research of the Center for Enzyme Engineering at the University of Portsmouth, as a senior research fellow. And then we were very glad, very happy, very fortunate to have Reynier to come to this our university and to our department as a Profesor Ayudante Doctor. I very much hope that this position will last not too much, and soon he will become Professor Titular. He will become assistant professor, which is something that he really, associated professor, which is very much he deserves. And that's all I can say. As you can see, he has a very, very important curriculum. And yeah, and as I say, also, I mean, I'm very, very glad that we were so lucky of having him in our department. So this is time for you to start to talk, and please, whenever you want, go ahead and you will tell me. Okay.
Okay.
Thank you very much.
Thank you, Javier. I just want to ask you if you can hear me correctly. Is it okay?
Yeah, we can hear perfectly.
Okay, perfect. So before starting, I just want to make some formalities. I just wanted to thank Maria Teresa for the organization of all this activity and the time taking. I also want to thank Javier for that kind introduction, and also the foundation for all the technical support and the platform and so on. So I will start sharing my screen. The title of the talk, I just want to say before starting that this is only an application of one of the many different lines of research that we have in the group. This is an application of on a specific system, an enzyme that is responsible for some kind of antimicrobial resistance, that I want to make clear that we are not experts in resistance of bacteria. We are computational chemists, and this is only one application that I want to bring to you today, right? So I don't think I need to convince you about the importance of this phenomenon. There is antimicrobial resistance, so I will be very quick. I think there is actually nowadays even some publicity in the TV about this problem. It's a global threat. It's something that could be really a problem. And I just want to show you some figures, some numbers for you to get an idea of the magnitude of the problem. There are, let me just change the pointer. There are every year around 60,000 newborn babies. Newborn baby means babies within 2 or 3 days after being born that die every year in India, only because some complications related to AMR, to antimicrobial resistance. 60,000 per year means more than 160 deaths of babies every day in India. And globally, in the whole world, there are 700 million people dying every year because of this problem. In Europe, we are doing better. We have only, let's say, only 25,000 deaths because of this problem. And those deaths are because mainly by 5 resistant bacteria. And if nothing is done, it's estimated that for 2050, there will be around 10 million deaths if nothing is done. And those deaths will be related to this problem, to antimicrobial resistance. That will cost around, well, this is in pounds, the number, but it will be around 70 trillion euros. This is a 70 with 12 zeros, so it's a huge number. So this is a huge economical problem. It's a huge health problem, and I would say it's a problem of life or death, right? So it's a very important thing. It could be even much worse than the current pandemic. And this is something that we need to tackle, we need to solve in the near future. So if we are computational chemists, so you may wonder, why are we studying this, or what we can do about it? So we want to contribute humbly in whatever we can to understand the mechanisms behind this resistance. There are different mechanisms for antimicrobial resistance. One of them is enzyme activity. Sometimes there are some enzymes that just attack the antibiotic and break down the antibiotic, the molecule. And sometimes these enzymes modify the target of those antibiotics and cause the antibiotic to be not effective. So I forgot this little green fellow that is supposed to be a resistant bacterium. Well, as I said in the title, we want to understand what's the mechanism of resistance to colistin. Why colistin? Colistin is a polysemy. Well, here we have the formula. And it's a type of antibiotic that is a polymyxin, and it's used against gram-negative bacteria. It's not actually a very good antibiotic, it's not a very friendly one, because it has many nasty side effects. For example, there is some kidney toxicity and actually some brain inflammation. And this antibiotic was discontinued in the 80s and was recovered, the use some years ago, well, actually, like around 20 years ago, because other, let's say, better antibiotics, for example, carbapenems, start to stop working, start to be ineffective against some multi-resistant bacteria. So this colistin is one of the, or remains one of the so-called last resort drug. Last resort antibiotic or last resort medication in general is a drug, it's a medication that you use when all of the drugs have already failed. So it's your last hope. So it's very important to know how this resistance arises and what's the mechanism that the bacteria use to be resistant. If we know the mechanism, we can design potentials, or at least we can start thinking about potential inhibitors for those enzymes. And if we stop those enzymes for working, then we can stop the resistance. So chemically, colistin is a cyclic polypeptide, as you can see here, and have multiple amine groups that at physiological pH, those amine groups will be positively charged. And then colistin will bind to the lipid A in the outer membrane of the gram-negative bacteria. As you know, gram-negative bacteria have two membranes, an outer membrane and an inner membrane. This is the outer, this is the inner membrane. And in the outer membrane, there is this component that is called lipopolysaccharide. And this is this is a saccharide in the upper part, and in the bottom it has a lipidic part. This lipidic part is the lipid A, that, as you can see here, is a glucosamine disaccharide that have multiple fatty acids, and very important is phosphorylated. It has two phosphate groups that at physiological pH will be negatively charged. As I said, colistin is positively charged, and this group here is negatively charged. So colistin will bind to the lipid A, and it will displace the cations, normally magnesium and calcium, that are stabilizing the membrane, are stabilizing this charge here. And then colistin eventually will provoke an instability in the membrane, and eventually will disrupt the membrane, will break down the membrane, and in that way the bacterium will die. So what's the problem with the resistant bacteria is that there are some differences in the chemical in the chemistry of this lipid A. Resistant bacteria, instead of having, you see here, the non-resistant bacteria has a phosphate. Resistant bacteria have a phosphate and alanine group attached to that phosphate. now the charge at the end of the lipid A will be positive instead of negative, and then the colistin that have also a positive charge cannot bind anymore to the lipid A and cannot make his job, basically. So we wonder how this phosphatidylamic group get there, and what's the difference between the resistant and the non-resistant bacteria. So a vital difference is that in resistant bacteria, there is an extra gene called MCR. Actually, that gene is present in plasmid in bacteria, so it can be transferred horizontally. There is a more efficient way of transferring genetic information between different bacteria. And this gene is expressed as a protein, as an enzyme with the same name. The name is MCR, that stands for mobilized colistin resistant. And that enzyme is the responsible for catalyzing the reaction that is putting this group in the lipid A and is conferring the bacteria the resistance. So what we know about this enzyme, and this is what we want to do. We want to understand how this enzyme is working, what are the details of the reaction mechanism, and most importantly, how can we stop this enzyme from working? So what we know already is that this enzyme have two domains. See, they have a catalytic domain, the first one that you see in the slide, and it have a transmembrane domain that keeps the membrane, the protein attached to the membrane, right? This is a phospholipid in the membrane, and this is the lipid A. So we have different crystal structure from my collaborators at the University of Bristol. They have obtained many crystal structures, and some of those crystal structures have two zinc ions, the active side, and those of them have only one zinc ions. Some of the crystal structures are phosphorylated in this threonine here. Some of them are not. So we have some experimental structural information that if we put everything together, we can think about a possible mechanism, and we want to study that mechanism and respond questions that could be, for example, how many zinc ions are used in this reaction, because we have crystal structure with one thing, we have crystal structure with two. What is actually the reaction mechanism? What is the reaction path? Is this mechanism, how many elementary steps have this mechanism? Is there any rate limiting step in the mechanism? What is the role of this metal ion that seems to have an important role in the catalysis? As I say, the most important thing at the end would be how can we stop this reaction to happen? But to know that, we first need to understand how the enzyme is working. So as I say, if we take all the information, experimental information together, we can think about a so-called ping-pong mechanism in enzymology. It's a quite common mechanism, also called a double displacement mechanism. Is when the enzyme has two substrates, and it works more or less in this way. You have one substrate that will be, in this case, a phospholipid, right? Not any, but most of the phospholipids present in the bacteria membrane can be a donor of this phosphatidylamic group, right? Because the most common phospholipid in bacterial membrane is this one. Let's call it PE lipid, and it has the group that is necessary to be transferred to the lipid A to confer the resistance to the bacteria. So the double displacement or ping-pong mechanism work in the following way. You have something, one of the substrate have some group that want to transfer to the other substrate, and what it does is to transfer first that group to the enzyme, right? Here, this phosphatidylamic group is transferred to the threonine 285, and that will be a first step of the whole mechanism. Then this substrate have to leave the protein and the second substrate has to come into the active side. So now we have a phosphorylated protein, a protein that is chemically changed, and we have a second substrate. And then the same group is transferred to the second substrate. In that way, we have a reaction that is basically impossible to happen without the mediation of the enzyme, and is something that is in principle very easy to happen, because in the same membrane you have the donor and the acceptor of the phosphodienolamine group, but that cannot happen without this enzyme. The enzyme is catalyzing basically that reaction, and that's what we want to study. We want to know all the details, all possible details about this reaction. For doing that, for trying to understand or to shed light into the details of that reaction, we will use two different techniques that are parallel. One of them is a cluster model, this one here. Cluster model is probably a very crude approximation. I will explain it very quickly now. And the other technique I will explain today a little bit, just roughly, is QMMA. QMMA is a more accurate technique, but is slower and it's more complex. It's much more difficult to do, actually. So, but before starting any of the studies with any of these techniques, we need a first approximation of the starting structures of the reactants of the reaction. To do that, we need to do a series of steps before starting with this, and I will just describe very quickly those steps, right? And this is because what we have experimentally is a crystal structure of the catalytic domain, of one of the domain of the protein, but the substrates for this reaction are in the membrane. So at least we need to know where is the membrane located, what is the orientation of the membrane regarding the protein. So then we have the sequence of the catalytic domain, but we don't have the sequence of the whole protein. So the first thing we do is to use basically a database. Actually, I want to, before starting that, I want to say this is not chemistry. This is just bioinformatics, and this is something that it's a tool that, some tools that we use before entering in the chemistry part. We go to this website that is called Uniprot. They have a lot of information about function, about especially about sequences of proteins. Then we put here the chunk, the part of the sequence we have, and we can find the whole sequence of this protein. So second step, if once we have the whole the sequence of the whole protein, we can do sequence alignments using there are different tools. The most, I think, famous and the most used is that one called BLAST. It will use an algorithm to find proteins that are similar, have a very similar sequence to use. And what we are looking for is a protein that have a similar sequence, but at the same time have a 3D structure determined. So we can find the sequence of another protein, but if we don't know the structure of that protein, including the two domain of the protein, is useless. So we will do this sequence alignment against, it's not working, against the PDB. The PDB is another database that is free, and it has most of the three-dimensional structures of protein and nucleic acids freely available. So we use BLAST against this database in a way that we can find a protein structure with a very similar sequence, and also with a 3D structure determined. So the next step we do is then an homology modeling. Homology modeling is based on the biological fact that when two sequences share a high similarity, their respective structures, 3D structures, are also similar. There are different, again, websites and algorithms to do homology modeling. We use this one. And what we get from here is a model, is a protein, sorry, that is very similar to our protein, but have the structure of the two domains at the same time. So we assume that the structure of our protein of the second domain will be very similar. So this protein that we found is extremely similar. It's actually a phosphatidylamine transferase, like our protein. That this is the mechanism we are proposing, is phosphatidylamine transfer. And this protein is also in a membrane. And we can use another database of orientation of membranes in proteins. And then we assume that the orientation in that similar protein will be the same orientation of the membrane in our protein. At the end, we will have an homology modeling. The homology model, let's say, it is actually the gray one, which is a calculation based on homology modeling. And we will have the orientation of the membrane in that template protein, in that protein that is very similar to ours. If we now align, if we superimpose our crystal structure with the homology modeling, we will see that they are very similar. So we will use a model that is a sort of a Frankenstein, because it will have for the catalytic domain the crystal coordinates, because those are experimentals and we prefer to use those before using the coordinates of the model. But for the second domain, we will use an homology model, and this orientation of the membrane will be also a model. We are assuming that the orientation in the two proteins are the same. So once we have that, we know where the protein is. So it's very easy for us to know where the substrate is coming from. We wanted to locate the direction of the substrate coming into the active site of the protein. So I think now we have everything to start doing a cluster modeling. So cluster model, this is more chemistry now. Cluster model is actually a quite old and general technique. I think it's very used in modeling of heterogeneous catalysis, but we can also use it for modeling of enzyme catalysis. And it's very basic. It's basically you select the most important residues, the most important amino acids that you think are vital for your reaction or whatever the process you want to model, and then you extract a cluster from that big system. Let's say that this is our protein. We decide these are the residues that are more important, and we extract those residues with the same geometry from the protein. It can be seen in another way. You just have the protein, you select the residues, and then you remove the rest of the system. As you can imagine, this is a very shocking, a very drastic approximation, because you don't have the protein there anymore. So we did our cluster model, and we know where the membrane is, so we can build a small molecule that will be a model of the substrate, a model of the phospholipid that is the first substrate for this ping-pong mechanism in the protein. Here we have the same thing, but it's a 2D representation. And for this structure, this will be our starting structure for our calculations. But if we intend to do any calculation in this structure that comes from a protein and had all the protein scaffold around, if we try to do that, then the system will span all these pieces of molecules that are not connected among them will start moving away. right? So to avoid that and to somehow mimic the presence of the protein, we have to fix some atoms. Normally, we fix the alpha carbon of the protein. For example, this is an amino acid, another amino acid, another one. So we fix the alpha carbon of the protein. And in that way, we are mimicking the backbone of the protein that is stopping the system from expanding, from moving away. So these atoms around the cluster model cannot move, but the atoms inside the cluster model can move. Again, this is a drastic approximation because atoms, even in the backbone of the protein, are not rigid, they are not frozen there. And actually, we are fixing all the atoms, but one alpha carbon can be, let's say, in a helix, and another alpha carbon can be loop of a protein. So the last one would be much more mobile than the first one, and we are fixing both of them. The other approach we can use is to not to fix the atoms. We can impose a harmonic constraint to the Cartesian coordinates of those atoms. So in that way, we can use a stronger force constant and a stronger constraint to the movement for the atoms we know are located in a helix, and a weaker force constant for the atoms that we know are located in a more mobile part of the protein. So here we have our cluster model, and here we have a model of a phospholipid. It's a very crude model, but this is basically to reduce drastically the size of the protein. And once you have these, let's say, small molecules, not that small, but when you have this small molecule, you can treat it like an organic molecule, not a biological molecule. And then you can use all the arsenal of quantum chemistry method that you have available. You cannot do that if you use the whole system, the whole protein. In some minutes, I will start talking about the QMMN. In QMMN, we keep the whole protein. Actually, we keep the membrane and everything. And then you will see there are also some disadvantages using that model. But here, the great disadvantage, the major disadvantage is that the protein is not there. And we are making many drastic approximation. One of them is, for example, that the dielectric constant inside the protein is completely different to the dielectric constant in a solvent or in vacuum. That is actually the way we are proposing to do this calculation so far. So we need to make a study of the how the dielectric constant affect the reaction, but I won't talk about that for the sake of finishing time. So this is our cluster model. Once we have this cluster model, we need to start testing all possible pathways driving the reactants to the product states. And here is when chemical intuition comes into play. You have to be a chemist to know which reaction path to choose. This is actually a very simple system. Sorry. And there are not many possible reaction paths, but in the different system can be around 100 of possible reaction paths. And if you are a chemist, you need to decide, you need to know which are those reaction paths that are more likely to happen. We have tested many of them. Here are some of them, only 3 of them that were discarded. They are discarded first because you may find maybe a reactant state for that reaction path, but you are not able to find a product state, and most likely you are not able to find a transition state for that reaction path. And the other reason to discard some reaction path is because you find all the stationary bonds or reactant, product state, and transition state, but the reaction barrier, the difference between transition state and reactant state is too high. Just want to show you this slide to tell you we have discarded many possible reaction paths. This second slide is or show two reaction paths. One of them is discarded because the reaction barrier is too high. It's around 36, something that is almost 40 kilocalories per mole is just impossible to happen inside a protein. So we discard this reaction path. As you can see, it was about this hydrogen being transferred to one of the option of the phosphate, and then getting transferred to the leaving group of the first substrate of the protein. This is another reaction path we found with, let's say, acceptable reaction barrier. Here, this hydrogen of the threonine is getting transferred to one of the carboxylate group, to this glutamic acid here. There is also nucleophilic attack of the option of the threonine to the phosphate group of the lipid. And there is also a transfer of one of the protons of this histidine that is protonated. It can be unprotonated, but we are assuming there is protonated. There is a transfer from this histidine to the leaving group that is helping the leaving group to stabilize and to leave then the binding pocket. So let's stick to this reaction path. So when you start the calculations, as I said, what you need is to find a reactant state, a transition state, and a product state. In the transition state, we found there is an imaginary frequency that corresponds to this animation of a normal mode of vibration that is connecting the reactants with the product through the transition state. I'm not sure if you can see it here, but this is the threonine. The threonine is this one here. It's transferring a proton to this carboxylate group here. This is a 3D representation of this. And at the same time, there is a phosphorus transfer from the substrate to the threonine, right? And at the same time, there is this proton that is getting transferred from the histidine to the leaving group. So everything is happening at the same time in this normal mode of vibration, and that make us to think that this step of the reaction is concerted. Everything is happening at the same time. Another option that we could find here is that the proton transfer is happening first, and after this proton is transferred, then this option here will have a strong negative charge, and that could help the nucleophilic attack to the phosphorus, or so on. So there are many options that you need to take into consideration. You need to consider. But this reaction path looks reasonable. We have found a nice transition state with a nice normal mode, and we think it is concerted this step of the reaction. I forgot to mention all the details of this quantum mechanical reaction, and I probably forgot to say also that the greatest advantage of cluster model is that it is a purely quantum mechanical method. Quantum mechanics is the proper theory you need to use to deal with a chemical reaction, because there are bonds that are breaking and forming. You cannot do that using molecular mechanics, which is the method, the preferred method for biomolecular modeling in general, for the modeling of biological molecules. So we use DFT here, we use B3 functional, and I won't waste a lot of time with this. The most interesting here is that we have used different basis sets for different atoms. We have used a larger basis set for those atoms that are directly involved in the reaction. You see, for phosphate and oxygen, and we have used a pseudo potential for the zinc atom. So this is the reaction barrier. This is the energy of reaction, and this is the reaction path for our first step. We need to do something similar for the second step. And something that I have not mentioned here is that, as I said before, we have crystal structure with one zinc and two zinc atoms. We have tried both, in all the different reaction paths we have considered. And this is the path that we think is more likely to happen because of the reaction barrier. And that path includes only one zinc atom. We have obtained other reaction paths using 2 zinc atoms, but they have a higher reaction barrier. For the opposite happens for the second step. We try very hard to find reaction path using only 1 zinc atom, but we couldn't find any of them. Any of them was very difficult to calculate, to locate the transition state. Nevertheless, it was very easy to obtain reaction path after you put a second zinc ion in the model. So what we think here is that for the first step of the mechanism, a single ion is enough, but the protein, the system needs a second ion to be able to proceed with the second step. So this is a reaction path we found for the second step. Now what we have here, the substrate is the lipid A. This is a model of the phosphate group of the lipid A. This is the phosphorylated, sorry, let me drink some water. This is the phosphorylated protein. And now there will be a nucleophilic attack of this opsin to this phosphate. Now the living group will be actually the whole protein, or at least this threonine here. And this hydrogen that was transferred to this carboxylic group in the first step will get transferred back to its original position. The reaction barrier we found here is much lower than the first step. So we can think about the first step being the rate limiting step of the whole mechanism. This reaction path is also concerted, is happening at the same time. So this is the whole mechanism that we propose, is, as I say, the ping pong mechanism. We think the first step of the mechanism is the rate limiting, is the one that is defining the velocity. If we take into account only the chemical reactions in this whole process, it can proceed with only 1 zinc atom, but not the second step. The second step needs 2 zinc atoms. And this is more or less a table with a summary. First step can proceed with zinc atom, cannot proceed, or at least it's very unlikely to proceed with 2 zinc atoms. But the second step needs a second ion to proceed. So the enzyme needs to recruit a second zinc ion that can be coordinated by the histidines that are in the very near in the active site, or can actually come bound to the lipid A, that is the second substrate. Well, we published this very recently, you see, just some months ago, and we got the cover of the journal. And actually what we wanted to say, we want to make clear that we think this is a ping pong mechanism. As you see, we draw there some ping pong rackets. The balls should be the phosphatidylamine group. And we let the question about how many zinc ions we need there open us with this interrogation mark here. Another analysis we did here that I will just mention very quickly was the role of the zinc atom. What we can do, something that we can do with calculations, with modeling, that is more difficult or just impossible to do experimentally, is to change very quickly the ions. We can put a zinc atom there and we can change it automatically with a magnesium or a calcium ion, or we can put there even a point charge. And that's what we did. We did the same thing. We tried to model the same reaction using a point charge, and we didn't get very different results. So we think this is something I could talk later, because I want to pass quickly to the QMMM part. We think the role of the zinc is basically structural. It's a positive charge that is there to keep in place all the negative charge. If we see very quickly, here we have negative charge here, negative charge here. This one is not negative, but I have a negative charge density. We have negative charge here. So we have many negatively charged groups very close in Spain. So we need a positive charge there to stabilize all the scaffold of the protein. And according to our calculation, the job can be done even with a point charge. So we think any metal with a size similar to zinc could do the job for this catalyst. Well, I will check quickly in the chat because I think people is writing here, but I can't do it. So I don't know why. Okay. So I cannot open the chat, but I see there are many people, there are like 5 questions, something there. I will stick to the talk and I will start talking about the QMMM approach. So QMMM is a completely different approach, but the advantage of QMMM is that we can keep in place the whole system. We can use the whole protein and even the membrane in our model, and we want to still use quantum mechanics. To do QMMM, we still need to do all these steps here. That's why those steps are common to both approaches. So to do QMMM, I will remind you, we have a catalytic domain. Is part of the protein. We have the second domain of the protein that is inserted, is a transmembrane domain, is inserted in the membrane, and we need a membrane. This, we already have this, but we don't have a model for the membrane. Building the membrane is not easy. I cannot say that, but it's not extremely difficult. Nowadays, there are some software and techniques for building different kind of membranes. The problem here is that we don't know exactly what is the local composition of the membrane in the bacterium. We know the global composition, but we don't know if the local composition can be different. So we have to try different compositions of membrane. We have tried at least three different compositions for the membrane, and I think the most realistic is one that have 80% of PE lipids, have 20% of PG lipids, and have a couple of lipid A's that we will need to model the second step of the reaction. So we can build our membrane, and as we are using QMMM here, and there is a part of the calculations that will be done by MM. MM is molecular mechanics, and as you know, molecular mechanics is a computational method that use potential functions to calculate the energy of the system, and those potential functions are based on classical mechanics. So we will use classical mechanics for that part of the system, and that is much faster to calculate. So we can use a big chunk of membrane for our system. So let's say we already build the membrane. The membrane is realistic. We need to put solvent there. Solvent in this case is water, but not only solvent, we also need ions to make the system even more realistic. And in this case, as we have a membrane that have many phosphate groups that at physiological pH are negatively charged, we will need to put many cations close to that membrane. So this would be our whole model. As you see, it's very different to the one in the cluster model. When I showed you the 2D representation, you probably say, well, that is a very shocking approximation. That's a very small molecule representing an entire protein. So here we have a big model. The protein is just there, hidden in all the membrane solving, and we can use this whole model if we use QMMM. QMMM, as you can imagine, stands for quantum mechanics and molecular mechanics. And the greatest advantage of this method is that you can focus in the most important part of your system. Let's say here in an enzyme is the active site where the reaction is taking place. And you can do that. You can focus there. You can use the highest available level of theory that you can afford, but without losing the effect of the rest of the protein or even the membrane, because you can keep everything there, but everything else will be treated using molecular mechanics, will be treated using classical mechanics, which is much more efficient, much faster. So QMMA intends to use the best of the both worlds, the accuracy of quantum mechanics and the efficiency of molecular mechanics. The setup, the configuration of a QMMA calculation, I won't lie, is much more difficult than the configuration for the cluster modeling. But let's say we already have done everything. What we need to do next? Well, we need to decide which is our QM region. The QM part of the calculation is that part that will be treated using quantum mechanics. And in this way, it is similar to the cluster model. You need to decide, you need to know which are the most important part of your system, or at least, well, actually, you probably need to try different sizes of your QM area, your QM region. You need to do the calculation many times, and you need to prove that if you reduce the size of your system, you still obtain the same results. But let's say we already did everything, and we already have our choice of QM area, of QM region for our calculation. So all these amino acids that are inside the square will be treated using quantum mechanics. You can see there is a size of a QM area that is very similar to the size of the cluster model. I'm doing that for the sake of comparison, just to be able to compare between one method and the other one. Also, the level of theory used for the QM calculations are very similar. We use DFT, we use B3 functional. The difference here is that we have used the same basis set for all the atoms. And then we have the QM part. For the QM part, we are using CHARM software and CHARM's phosphate. CHARM is one of the most used software and phosphate in protein simulation. And we are using an electrostatic embedding scheme. I don't have a lot of time to talk about all the detail, but this is important. Electrostatic embedding scheme means that when you are doing your QM calculations, you are in the QM calculation, the MM part, the rest of the system is present there in the form of point charges. So the MM part can affect and can polarize the QM calculation. So it's a much more realistic type of calculation because it's taking into account the effect of the system. We are using hydrogen as linked atoms. I can talk later about this if you want. And once we have this, we have got this long molecular dynamic simulation just to see, for example, how the lipid A diffuse throughout the membrane. But for doing QMMA, actually it's not convenient to do very long molecular dynamics because the structure of the active site can move away, can be very different because of the dynamic of the molecular dynamics, very different to the crystal structure, and we don't want that. We want to keep more or less the relative position that we have in the crystal structure. So we did only 50 nanoseconds of molecular dynamics before doing QMMN. This is classical molecular dynamics, and we kept this membrane composition. So another thing you need to do, you need to decide in QMMN is your reaction coordinate. In DFT cluster models, we were calculating reactant, transition, and product state. Actually, I forgot completely. In DFT cluster model, after you have the reactant, transition, and product state, you need to do an ERC, an intrinsic reaction coordinate calculation to see if actually those 3 points are connected in the same surface. Here, you don't have to do that because you will define a reaction coordinate. Reaction coordinate can be anything, can be anything that is variable in your system. Most common is to use distances, but you can use angles, you can use dihedral, you can use even charge changes and charge progressions. What we have done here, what we have used is a linear combination of different distances, as you see here. Those are the distances between atoms involved in the breaking and forming bonds. Here we have in blue color, for example, the distance between oxygen or threonine and hydrogen of these, of the same threonine. Actually, this is this bond. It's the distance between this oxygen and this hydrogen. And then we have a minus sign and the distance between this hydrogen and this oxygen here. This is positive because this bond is breaking, and this is negative because this bond is forming. So as we know the geometry of the reactants, we can calculate the value, the actual value for this reaction coordinate in the reactants, just doing this calculation. And we can tell the program, well, I want the energy of this system at this value of the reactor, of these reaction coordinates. So the next thing you can do is just to increase a little bit this value. Let's say this value is -2, now it would be -1.9. So the optimization algorithm will accommodate your system in such a way that we'll find a minimum energy for the reaction coordinate to be in that new value. That doesn't mean that it will constrain these distances. These distances are free to move. They are all free to change. The one thing that is constrained in a value is the reaction coordinate, okay? The global value of this reaction coordinate. So we do that for 1.9, -1.8, and so on. And if the reaction coordinate have been properly selected, we will get from reactants to our product state point by point, right? And here we don't have a transition state. We don't have an activated complex, but we have a highest point in a reaction profile. So the structure here should be very similar, should be close to our transition state. And in this way, we can calculate something similar to what we calculated in the FT cluster model, which is our reaction barrier and our reaction energy. As you see, the reaction barrier here is 20 kilocalories per mole. In the cluster model was 21, if I remember well. So it's very similar, and they match. What is not similar is this reaction, the energy of reaction here. So another thing that is very convenient to do here is to let the protein to adapt to this reaction profile. Let me see how I explain this. So what we do in practice is we scan the reaction coordinate forward from reactant to product, and we scan backwards the reaction coordinate from product to reactants. When you do that the first time, you will get something like this. Let me try to do this. I don't know if this will, I don't know how to do this, but I will try it. So your first scan of your reactant coordinate was something like this. When you do the same thing backwards, you will have something like this. And yes, you will have some hysteresis here. So the reaction profile won't be the same. And that is because you have many things, many molecules, moieties of the protein around. And when everything here is changing, the interaction with the rest of the protein change too. And those molecules have the orientation optimized for the reactants, not for the whole reaction profile. So I don't know if I make myself understand. But if you keep doing the same, you do again your reaction and do it again, backward and forward, eventually you will reach a convergence. And that convergence, well, it's not a very good drawing anyway. That convergence is your converged reaction profile. And in that reaction profile, if you take the structures from that specific reaction profile, then you will have your system, your protein, adapted to the whole reaction profile. The idea thing to do here is not to do this, is to include dynamics on each of these points. Is to calculate this energy, but including the movement of the rest of the protein. But that can be done. We can do a QMMN, which means QM, quantum mechanics, molecular dynamics. That will be a Bohr-Benheimer molecular dynamics, but it can be done. We can do molecular dynamics for each of these points, keeping constraint, keeping, let's say, frozen, but constraint. It's not frozen, but because it can change a little bit, this value. And in that way, we can include the effect of the dynamics of the protein on your reaction profile. But this is it will take a very long time to sample all the possible values of the reaction coordinates. So we can use advanced sampling techniques. One of them is umbrella sampling. Umbrella sampling is a method in computational physics that is used to sample systems that suffer from poor sampling. This poor sampling can be caused by a high barrier between two minima, for example. And this is actually what is happening in a chemical reaction. We have two minima and we have a high barrier in between. So if we do umbrella sampling for this, we get the line in black. As you can see, it's very similar to the line in blue that was without including the dynamics in the calculation. So we can say that the effect of dynamic is we can ignore the effect of the dynamic here, although we have done a very short time of sampling. We have done 1 picosecond of molecular dynamics for each of the points. But this is not the most important here. Well, after the umbrella sampling, of course, you can recalculate the reaction profile and reaction energy. And this time, as you have been sampling the different parts of the system, you can calculate populations. And from populations on your partition function, you can calculate directly free energy. That's another advantage of using advanced sampling techniques. You don't calculate potential energy, you're calculating free energy directly. And I think I'm not doing very well with time, actually, but I will talk about this very, very quickly. This is some analysis that we can do from the umbrella sampling or the dynamical simulation of our system. What I have done here in this graphic is to put in the X part here, the phosphate cleavage. That means the part of the reaction coordinate that is related to the phosphate cleavage, that are these distances, I think, right? And in this part, I'm putting the part of the reaction coordinate that is actually is more, but I don't see here because I have my face just in that part of the presentation. So actually, yes, these two distances are here, and this is in this part. These are the distances related to the hydrogen transfers, and these are the distances related to the phosphate transfers. And this analysis will give us if the two processes are happening at the same time in a concerted way or in a stepwise way, if one of them is happening before the other one. Let's analyze first. I think we will understand better if we consider, for example, that the hydrogen transfer is happening first, right? And secondly, in a sequence, after the hydrogen transfer happens, then the phosphorus transfer happens. So let's consider that. If that is true, then these distances, this one and this one, will start changing, right? But these two distances will keep a constant value, or more or less a constant value, because this phosphorus transfer is not happening. So this distance and this distance keep the same, right? So it keeps the same. Let's say this value and the other distances start to evolve. At some point, this hydrogen will get transferred to here, and after that, this oxygen will make a nucleophilic attack. So these distances will start to change, and then we will have something like this. This distance will not change, and the distance that will change will be the ones involved to the phosphorus, right? But we are not getting that. We are getting more or less a diagonal line. That means that this process is happening at the same time to the other process. If we do the same, but now with the phosphate distances and the other hydrogen transfers, we will see something similar. So if this hydrogen transfer is happening at the same time as the phosphorus transfer, and also this hydrogen transfer is happening at the same time, so the three processes are happening at the same time. This is the same we found in DFT cluster model, that the first step of the mechanism was concerted and all the two hydrogen transfers and the phosphorus transfer were happening at the same time. Well, we confirmed that here, and I will actually finish in the next talk. But I want you to notice something that I have just talked about the first step of the mechanism with QMMA, and that's why we haven't started to study the second step of the mechanism, which is more difficult because the second step involves the lipid A, which is a much larger group. But this is something we are working on it. Actually, we have already results. They are similar to the ones we obtained for DFT cluster model. And that's it. That's what I wanted to show you is there are basically two techniques. They can be complementary, or you can use one of them if you want a quick result, if you want results very fast, that is cluster model, or you can use a much better technique, a much realistic technique that is QMMA, and you can combine different level theory to tackle the problem, to deal with specific problem. And this will be my final remarks or conclusions for this. We have proposed a reaction mechanism for lipid A modification in this MCI1, which is the enzyme responsible for antimicrobial resistance to colistin. The reaction mechanism have two steps: the transfer of phosphatidylamine group to the membrane, from the membrane, to the threonine 285, and the subsequent transfer of lipid A, the subsequent transfer of that group to the lipid. And we did that. We got that conclusion, we drew that conclusion from the DFT cluster model. We think the rate limiting step is the first, and we also think there is a concerted chemical step, this first step of the mechanism. And we got that from DFT cluster model and from QMMA2. First step of the reaction is feasible, can happen using only one zinc, and one of the histidine have to be protonated. As I said, we studied the role of the zinc atom. We think it's only structural. And the second step of the reaction, which is very important, needs a second zinc ion to proceed. And this is very important when it comes to designing inhibitor for this enzyme. For the calculations are in progress, so this is not this is an ongoing work. So I will stop talking here. I think I have talked too much, and I will pass the word to the moderator. So Javier.
Thank you very much. It was very nice, interesting talk. I hope that we can get some questions from the audience. I mean, is there anyone that wants? I mean, you can. I think there is access as well for microphones. So if you want, just use raise your hand, and you can put your question also in voice. You can talk to, not necessarily just sending a chat.
I don't know if I can ask a question, because I have I'm not an expert in this, but I want to ask you a question. I mean, I think that it was a very interesting talk, and I mean, you talk about a model of a active site in this enzyme. How do you which is your expectative in order to prove that these amino acids are involved in the active site? You are going to do some kind of mutants, or you are going to express this protein? I mean, because sometimes you need to prove that this mechanism is that way with an experimental model, an experimental protein. No, I don't know if it's something that you are going to do in collaboration with some group or whatever. Another question is, you were talking about the mechanisms, but I think that which is your I don't know if I understood correctly, but I think that you have a model of other protein that is in the PDB. It's related with this one. This one is a homologous protein, but it's not exactly the same. It's not the same enzyme. Then how you are so sure that you have two things, that you have one cation or two cations in this mechanism, or whatever, if you don't have any model to follow to prove your observations?
Yes. Okay. I see your concerns are related to the experimental part of the project. As you said, yes, I work in collaboration with an experimental group, with actually two experimental groups in Bristol, and they have done many other things, much work that I have not presented here. I just presented the computational part. And they do, for example, all the crystallographic work. And they also do, for example, I don't know, zinc deprivation experiments. They eliminate zinc from there. They do NMR. They do, for example, how do you call this? Chemical shift maps. When you change something in the protein, so you have some NMR fingerprint, and without the same change in the protein, you have another map in NMR, and then you see the changes.
But Reynier, one question. I mean, the crystallization of the NMR structure is made with the catalytic, with the whole protein. No, it's only the extracellular. The extracellular domain.
Exactly, yes. Only the catalytic domain. Okay. That's why all this bioinformatics thing to construct a model with the whole protein. Okay. And I think the short question is that we will never be sure about everything until we have more experimental proof. What we are doing is to try to understand, to try to shed some light there. And for example, the next step is to finish with the second step of the mechanism and see how the lipid A is diffusing in the membrane. There are many things to do. But after that, what we have to do is to start trying to design inhibitors for that protein, trying to say, but it's not that simple, because there is something that have to go through two membranes to get to but experimentally we can do that somehow, and the inhibitors we are proposing are doing something that would be a first proof that our mechanism have something of truth there. There is truth there. And the other thing is that it's a very new protein, but this protein is expressing E. coli in one bacterium, but the other protein that is in the PDB is in a different bacteria, but they are very similar. So they are different proteins, but there are a lot of similarities. So we can expect to happen the same in our protein. And that protein is the specific protein that we found in the PDB to use it as a template. This is phosphate-anolamine transferase. So that is what that protein does, and have a structure that is very similar to ours. So it's normal to think that our protein will do the same job.
Okay, thank you very much.
You're welcome.
I was going to ask more or less precisely the same question. How do you choose precisely the clusters, so the pieces of the molecule that will contribute to that? And you say this is very much based on experimentation, right? So you have to rely on people that can tell you this is going to be about that. So it's no predictive part in the work that you can say, okay, I know that it's going to be this, and this. And so I mean, I think this is you already answered what was my question. My next question was, why zinc? Why was zinc and no other, for instance, calcium? It is because this is the size of the cation, or it is because the zinc has the orbital, so it can make rather better coordinations with everything.
Okay, so the first question is the most difficult to respond, and I will tell you the truth. The good practice here is to choose different sizes for the cluster model. So to choose a very long size of the cluster model in such a way you are sure you are including everything important for the reaction, and then do some calculations. And then start reducing the size of your cluster and check if you are obtaining the same results. And after some size, you will realize that the size is too small and you cannot reduce the size anymore. So that's your limit. And that everything is based, as I'm saying, in the computational part. Of course, if you have experimental information and you know there is some residue that is vital for your reaction, you have to keep it there. But normally those residues are very close to you. They are in your active site, so they are not very far away from there. So if you don't rely on experimental information and your cluster is big enough, you will include all the important residues anyway. But what you have to do is that you get a big cluster, then you calculate one reaction. You don't do all the job with that big cluster. Then you start reducing the size. And once the result started to change very much, then you know that's your limit. Then you know you cannot decrease the size anymore. I think that's the first question. The second question is have two answers. The first one is very easy. Why zinc? Is because it is in the protein. Experimentally, it's proof that zinc is the ion that used the protein to do the job. So we do the calculation with the same cation. So that's for sure. What we wonder if the enzyme can use another type of cation, let's say. But this is something that is we a chemist or maybe physicist ask about that because it's just interesting. Let's say can the protein use magnesium? Because magnesium is very available there. It's in the membrane, and that's something that we wonder. And the answer generally is no. The protein is optimized by nature to use that very specific conditions. But we still want to understand what's the role of the zinc ion. And what we are getting here is that it's independent of the orbitals and they're independent of the cation you put there, because when we do the calculation with a point charge doesn't have orbitals, there's no atom there, there's nothing there, it's just a point charge in space. We get similar reaction barriers and we get similar structures. So a point charge theoretically is doing the job. So we think the role of the zinc ion, even being zinc, it has to be a zinc, but the role there is just structural. It's just keeping things in place. It's not doing, for example, it's not helping to transfer some charge from one part of the protein to another one, or is stabilizing some specific type of coordination. Actually, coordination in enzymes, zinc have a tetrahedral coordination normally, but it can have a 5 coordination or 6 point coordinations. But it's not about that. We think this is only a proposal. We think the role of the ion, of the zinc ion, is only electrostatic.
But if you do the simulations with another, it's so simple. Actually, if you have a point charge, it doesn't matter whether you are talking about calcium, magnesium, or zinc, right?
It can be done. It can be done perfectly. Yeah. Yes, it can be done.
But for sure, the enzyme is not going to be so efficient if you put calcium or you put another cation. Right?
Yes, that's the first thing.
Yeah, the rate of the reaction is important in this case.
The whole point is why is zinc, okay? This is like when we the nature is this is misleading because take artificial intelligence, okay? They can do the folding of proteins very nicely, and they can predict beautifully, and many thousands, and possibly.
Exactly, but they don't know why.
Yeah,
Exactly.
but they don't know how that happens, right? And
Sure.
and of course, this is, of course, we could apply artificial intelligence here and say, okay, zinc should be the cation, the ideal cation, but I mean, as a chemist or as a physical chemist, if you want, we want to know what is zinc and why it's not any other element. That's it. And I guess that if you change zinc by anything else in your simulation, nothing will change, right?
Well, it will change probably if the size of the cation change too much.
Okay.
If it is bigger, then you will just disrupt, you will destroy the active site.
Yeah.
But if it is smaller, it can work. And if it is smaller, I can have the same coordination, the same number of coordination. It could work, I think.
I think that it's a very interesting and fascinating conversation, but we have to stop now because it's almost 2 o'clock in the afternoon, and people in the foundation, I think that maybe are a little bit worried about the length of the talk. Then I think that I thanks a lot. I think that was a very nice talk and very interesting, and I think that I hope that we have more talks like this in the next year, in the next semester. And then until that moment, I said goodbye to everybody. Thank you for your attendance and see you for the next talk. And thank you, Javier, for your your role in this talk. Thank you very much.
Thanks.
Okay.
Bye.